In the previous two sessions, we have looked at application of matrices in chemistry and physics. Now let's look at its application in geometric transformations. So let's say we have this x-axis and y-axis. Let's have these two basis vectors on those axes, and let's form a grid based on this basis vector. Let's apply the identity matrix to this grid. So what is identity matrix? It's S equal to 1001. So what we are looking at is the identity transformation. So let's apply this transformation. So we have, since it is identity, it doesn't change. They remain as they are. That was identity transformation. Let's look at scaling transformation. Scaling transformation basically scales the vectors. Okay, so k sub x, if we change it, it will scale the vectors along the x-axis. Similarly, along the y-axis. So you notice the original basis vector is this, and the transformed basis vector is now this purple one. And the grid also has changed. You see, green and orange. Now let's make this back to 1, and let's change the last element, that is k sub y, as 2. So here this has changed, or rather it has got scaled. If we make both of them 2, so if I change it randomly, you see, along with the vector, the grid also changes. Okay, let's bring it back to 1. So that was scaling transformation. Now, the next is shearing transformation. So here, this remains 1, and we have S sub x and S sub y. S sub x gives us the shearing in the x direction, and S sub y is the shearing along y axis. So let's change this 0 to, let's say, 1. So transformed vector is along this direction. Okay. Now let's change it back, and let's change the third element, that is S sub y, to 1. Okay. Let's change both. What has happened? One of the dimension squeezed onto the remaining axis, transformed axis. Let's again take it back. So that was shearing transformation. Now let's look at rotation transformation. So rotation transformation is a matrix composed of cos p minus sin p, cos p. Now let's say this is, to begin with, let's keep the angle as 0. And now let's apply the transformation. Now since the angle is 0, we have 1, 0, 0, 1. Cos 0, 1, minus sin 0 is 0, sin 0, 0, cos 0 is 1. And let's apply the transformation to the vectors. Now, let's change the angle. If we change the angle to, let's say, pi by 6. So here we have a 30-degree angle, here we have a 30-degree angle. That means it has rotated anti-clockwise by pi by 6. So the entire grid has changed. Let's say pi by 4. Similarly, pi by 6. And let's say pi. So that is rotation transformation. Now let's look at translation transformation. Now, for identity, scaling, and shearing and rotation transformations, we had 2 by 2 matrices. But for translation transformation, we require a 3 by 3 matrix. Why? Mainly because in all of these cases, the origin remains fixed. Whereas in case of translation, the origin is also supposed to move. So that is why we require a 3 by 3 matrix. Okay, so let's start with this. And here you will notice that the top left block of the matrix is the identity transformation. Now let's bring in the original identity transformation, and let's bring in the transformation related to translations. Okay, now identity means it remains where it is. Now let's change dx. So let's say we change it to 2. So you notice that both the vectors have shifted to the right along the x-axis by 2. Similarly, if we change dy by 2, or dy is equal to minus 3 dx. So we say that this is the translated version of these two vectors. Along with just changing dx dy, we can also change the k sub x, k sub y, s sub x, s sub y. So in which case we say we are taking care of composition of transformations. That was looking at geometric transformations using vectors. That's not very interesting, right? So let's look at it using a picture. Now I'll not bother with the grids because you have already seen. Remember, in the background, the grids will be changing. So identity transformation is the original setting. Now let's apply scaling transformation. So this picture is there. Let's apply the identity transformation. It remains where it is. Now let's change some values. Yes, the original picture is there. This is the transformed picture. So this is in the x direction. Look at this matrix and look at this matrix. Here dx dy doesn't change. That is why it remains on this along the origin. Okay. Now if I change along the y-axis, now shearing along the x-axis, and now shearing along the y-axis. So this is a composition of different transformations. What are the transformations? We have a scaling along the x-axis, we have scaling along the y-axis, we have shearing along both x and y-axis. Let's bring it back to the original position. Now rotation. So here the angle is pi. If it is pi by say 4, this is how it looked like. Now let's look at translation. Yes. In summary, for a given transformation, if a direction in the photograph remains unchanged after the transformation and only its length changes, then that direction is called an eigenvector direction. Under certain transformations, a two-dimensional object may collapse into a line, which we saw. This occurs when the transformation completely eliminates one independent direction, causing the matrix to have determinant 0 and an eigenvalue equal to 0. If the photograph collapses further to a single point, then both independent directions have been eliminated. In this case, both eigenvalues are 0. That was application of matrices in geometric transformations. That's it for now. Bye.